Dating to start. I don't have to remind anyone, I think, of the brilliant history the UK has had both in spectral theory and in mathematical physics. In some ways, Sir Isaac, as in Newton, was the first spectral theorist because he famously said it's useful to solve differential equations. I can't tell you this in Latin, but it's always funny to see that he wrote somewhere it's useful to solve differential equations. Indeed, it is. I will start off, since my title has the distorted Fourier transform in it, I will remind you of what that is, and I ask the experts to please bear with me. So let's start off with this is the free Schrödinger equation on the line. Well, we will add a potential, and of course, we want this to be self-adjoint on a suitable domain. And what assumption are we going to make on V? It is convenient to assume that V is in L infinity on the line, as well as that we have bracket X. This is called the Japanese bracket, even in Japan. And it is root 1 plus x squared. You will see in a moment why we make this assumption. So then we have the scattering problem. We want to diagonalize H. So of course, H0, which is minus dx squared, is diagonalized by plane waves. So we have this. And there is a convenient substitute. That is why we make these assumptions, especially the decay assumption at infinity is important for what I'm about to say next. We want to seek these solutions that are perturbations of plane waves, because our operator is a perturbation of this, sorry, H with potential. And they behave asymptotically free, meaning that as x tends to plus minus infinity, they look like plane waves, and they are solutions of the eigenvalue equation, if you want. These are called Jost solutions. And the picture that somehow tries to capture what's going on, imagine you have an incoming wave, it is reflected and then transmitted. So imagine that after some form of scattering process that we do not describe, what comes out here as transmitted wave is the transmission coefficient times something that is asymptotically free. And the incoming wave would be F minus, but minus psi, of course. And then we have a reflected coefficients for the reflected wave. And F plus minus form a fundamental system. Here, psi is real, even though it's also very important to take them, for example, in the upper or lower half plane. But for now, psi is real. And then this is an identity. So to write this down again, this equals F minus psi plus the reflection coefficient, which is R minus. And this is an identity that holds for every x, which I'm suppressing here. And together with this, maybe I'll write it here, we have, with the same transmission coefficient, the analogous identity, symmetric identity on the left. So this would be the sum of F plus minus psi plus R plus psi, F plus psi. So there is a conservation of energy going on here, which is also known as unitarity of the scattering matrix. I won't go into that. Now, this transmission coefficient obeys an important identity, the Wronskian of F plus and F minus, plays an essential role. Since we have this identity, we see that this always has to be less or equal 1 in absolute value. In particular, this denominator here is not 0 if psi is not 0. And I will have something to say in a moment about what happens when it does vanish, which can only happen at 0. And in fact, that is important in nonlinear applications, to which I will get to in a moment. That's why I'm going into this, to show you then how to use it in certain nonlinear viscosity. But what is the distorted Fourier basis? It is given in complete analogy with just the standard Fourier basis, transmission coefficient f plus psi, if psi is positive or greater or equal 0, and then t negative psi, f minus negative psi. So if you look at this somewhat strange definition, because it's not the same for positive psi and negative psi. What is lurking here in the background is a Hankel contour that surrounds the spectrum, which is 0 to infinity. So this is a Hankel contour, and we parameterize this Hankel contour by psi squared, and then it matters if psi comes, right? That is why we have this seeming disparity here. Notice just from what's on the board. This, of course, gives you back the plane wave e to the ix psi when v is 0 in the so-called free case. Let me make a definition and lemma. TFAE, the following are equivalent. The Wronskian vanishes at 0. The transmission coefficient at 0 is not 0. There exists a solution to this equation. Phi is not 0, of course, and phi is in L infinity, but not in L2. In fact, that is automatic. Okay, I do not have to say that 0 is not an eigenvalue. Cannot happen under this condition, because under this condition, a fundamental system of this equation of the kernel, asymptotically, it has to asymptote the linear combination of x and 1, which is the fundamental system of H0, the free case. And if you're a linear combination of these, you can never be in L2. So what's let me elaborate on this, maybe not as a separate TFAE item, but here the picture that's really worth keeping in mind. Imagine that's your potential. What is a zero energy resonance? Why is it so called? Well, because you send in a constant from the left, it does something here, and it comes out, it asymptotes to another constant. It cannot asymptote to something that grows linear. That is why it's called a resonance. And resonance is, there's a little bit of a pet peeve of mine. Resonance means small divisor. Where is our small divisor? Well, it's here. If you do h minus z squared minus 1, so you look for the Laurent expansion of h near z equals 0. You take, for example, im z positive, so that this energy is in the resolvent set, this thing exists. Then it will start off, my red line here gets in my way. It starts off in this fashion. Phi tensor phi plus big O of 1. Where is this big O of 1? In some weighted L2, as z tends to 0. All right? If phi were, what's impossible, an eigenfunction and 0 an eigenvalue, then you would have 1 over z squared. But this resonance is a weaker small divisor. And all of these are called zero energy resonance or threshold resonance. Why threshold? Because under our assumptions, the spectrum of H has to look like this. Forgive this wiggly line. Here is the absolutely continuous spectrum. And then you can have a bunch of discrete spectrums. So eigenvalues of finite multiplicity on the negative axis. And then this point may or may not be the threshold resonance. Will they come up in nature? And what is their dynamical, how do you see a resonance in the dynamics in the Schrödinger evolution e to the ith? We'll get to that. So what do I do with the boards? Let me move on to nonlinear equations. So there is more to say about distorted Fourier transform. Please.
I'm going back to the very, very beginning. L infinity. So you assume that the
L
first
infinity is not so serious.
That's what I'm
It's
saying.
not serious.
You don't need it.
I don't need it at all. It was a bit silly of me to add it. It's just to distract if there are questions about local singularities. Yeah, so L infinity avoids local singularities, but this is enough. Yes, of course. Because of the Volterra equations that you have. Yeah. So nonlinear applications, if you want, but I'll just say nonlinear evolution PDE. Let me illustrate sort of what I have in mind by means of 3 examples. This is the strangely named Sine-Gordon equation. So this is Sine-Gordon. This awful terminology is too ingrained to try and change it by now. One could spend many lectures on this alone. This is old. It comes, I think, from the 1860s. Maybe somebody knows the name of the French Maciek. Do you know the French geometer who introduced this around 1860? This is the Gauss-Codazzi equation of the Beltrami surface. Let me attempt to draw such a thing. The hypersphere is the surface of revolution, singular here, that has constant negative curvature -1 hypersphere. If you write the first fundamental form in such a way that the first fundamental form is du squared plus dv squared, and then you have a cross term. I'm a bit hard pressed to remember what it is, but it's of this shape. In that case, maybe I got it wrong. This is a sine or something, but it looks somewhat like this. Then this is the Gauss-Codazzi equation of that. So let me erase this because it can be thought it's incorrect. Where's my eraser? Up there. It's a completely integrable PDE. So let me record that. It has magical properties that I might sketch. So what am I talking about? Ah, there is also an eraser hiding. Magical properties. So it has the so-called kink solution, which I will write down. It has breather solution. It has wobbling kinks. So a whole plethora of remarkable special solutions. There is some kind of vague meta conjecture out there that in some class of PDEs of this type, Sine-Gordon is unique with this property. And I will cite some evidence towards this fully formulated. Now, another big player in this arena of PDEs is this nasty one. And this might strike you as odd. The signs are correct. I've written them down a number of times to know that they're correct. I've also seen them in print stated incorrectly, like this. Kind of amazing to see this referred to as phi-4. So what is this? This is the famous phi-4 equation. Let me get rid of that. And this is cubic. This is nonlinear Klein-Gordon, NLKG, nonlinear Klein-Gordon cubic. So how strange that we just flipped the signs. I will write down the conserved energy in a moment. All of these are Hamiltonian PDEs. Why is this strange? Because if you think like a microlocal analyst, you want to look at the symbol. The symbol of this is xi squared, but then you have to subtract 1. Xi squared minus 1 means for absolute xi less than 1, you change from hyperbolic to elliptic. This something catastrophic happens. What does this mean? It means that the zero solution here actually makes no sense. Here the zero solution is perfectly fine. This has the right sign. This is a positive mass term. So this is plus xi squared plus 1, wonderful. Now these three models each have solitons. In fact, the first two have topological solitons. I have to part with my wonderful zero energy resonance board. I have another set of boards hiding over there. Tempted to use them. Can everyone see if I use those boards on the very left? Or should I avoid?
There are also some boards on the back.
Boards in the back? I will get hopelessly confused. Do that, but so the first one, Sine Gordon, is some form of PDE built on top of the physical pendulum. Why? Because all of these equations are of the form where W is a potential energy. So for the first one, W of phi is the potential energy of the physical pendulum. For phi 4, so this is Sine Gordon. Phi 4, we pick, you need a pointer. We pick the famous Ginzburg-Lambda potential. I'll picture in a moment. And this one is a bit different, so I'll leave that out because the first two are really field, as one says, they come from physics, field theory models. And the third one is just from the family of Klein-Gordon equations. Now, associated with these equations, there is a conserved energy, which is 1/2 phi t squared plus phi x squared plus w phi 0. Oh, sorry, dx, not 0. Okay, and this is an integral over the line. This is constant. As you can immediately see, just put a dt inside, integrate by parts on this term, and out you get that, okay? And notice that when you plug in phi equals 0 for phi 4, you would get 1 or quarter. This is both 0 or quarter, so the zero solution has infinite energy for phi 4. Now the picture of this, this is bad. It's supposed to touch here at -1 and 1. This is W for phi 4. I don't think I have to draw for you the level surfaces of the, or rather the graph of this, but we're interested in the phase portrait. Why? So if I were to look for time-independent solutions, stationary solutions, which in physics are popular because there's some form of bound state, right? So eliminate this. Look at the phase portrait for this guy. You will get a picture like this. It should be perfectly symmetric. Mine is not. Give me. So this is the phase portrait in the phi prime. So phi is phi of x. There is no t now. And as you can see from this picture, there are two red Hagoromo. I don't know if you noticed, but one way for our profession to get into the New York Times is through chalk. Because the New York Times had an article on these chalks, on Hagoromo chalk, and how our profession loves them. So this is not a great picture, despite the great chalk. So here is what one calls an heteroclinic orbit, two of them. They connect, of course, physical pendulum. They connect, you see, in infinite negative time, you come to the unstable equilibrium at rest. Then you go around and you reach it again in plus infinity, in positive infinite time. That's the heteroclinic orbit that I drew in red. Understood? And so this is the famous kink solution. If you look at the Cambridge text by Manton and Sutcliffe is, the whole book is called a topological solitude. So this is a topological solitude. It has an amazing formula. There are a lot of amazing formulas for these field theory models, these two in particular. So this is the stationary solution, and this is called kink solution. Why is it so called? Because it connects these two equilibria, the ground states, constant, connects them, and as one says, these have non-trivial charge, whatever this. You go from -1 to 1. I have to keep an eye on time. Where is the So here we also have a kink solution. This is the sine-Gordon kink. The 5-4 kink is also k of x. And let's see, it is tanh of x over √2. Oh wait, sorry. This is not that, because this connects 0 to 2 pi. So I just talked myself here into some kind of mess. This is the phase portrait of the pendulum. And you have infinitely many of these kinks because you can shift x here by 2 pi, or rather pi, the angle by 2 pi. This is the phase portrait of 5-4, and the tanh is the one that connects -1 to 1. My apologies if I confused anyone. So here we have a kink solution. Here we have a kink solution. And since I still have the hypersphere there, the kink solution has a particular relevance for this picture. Now since I also have it on the board, this doesn't have as much as a kink. What happens here, the phase portrait of the stationary solution looks like that. It connects, so there is nothing connecting -1 to 1. And here the soliton, which is not a topological soliton, is a homoclinic orbit that connects 0 to itself. And it is q of x is √2 sec x, if I remember correctly, okay? Now, big open problem. I think it's fair to say that's a big open problem in a certain community. The most famous for these field theory models, nobody knows if the kink for 5-4, I'm pointing at the kink, is asymptotically stable. So what would be perfect theorem? Take a small, suitably decaying, say in some weighted Sobolev space, odd perturbation of this, and prove that the solution phi then relaxes in L infinity back to k. All right. So the open problem, and what I'm erasing here, this distorted Fourier transform, is a favorite tool in addressing these asymptotic stability problems. And these magic models, which are that's two most famous, I think, examples in an infinite family of such field theory models, they have explicit Fourier bases. It's kind of magical. Sine-Gordon is completely integrable. 5-4 is not completely integrable. So here is an open problem. Why? So phi at time 0, and so this is time 0, so 0x is the kink solution, which is tanh of x over √2 plus some small u of x here, 0, and the time derivative of phi, you can either take 0, that's good enough, or you say that u0, u1 in some weighted Sobolev space, so we can write these as HSK cross HS -1K is less than epsilon. S is the number of derivatives, K is the power of the weight. So typically what we put here is 3 or 4, all right? That simply means that you can absorb a weight like this, x to the k times u0. So I might as well have written x to the k and omitted this so as not to confuse everybody. So then prove or decide, true or not, we don't know, that u of t and x minus k in L infinity tends to zero. But of course, we wouldn't just want to show that it tends to zero in L infinity. We want some rate. The optimal rate you can hope for is t minus a half as time tends to infinity. Now, as it's written, you will tell me this is impossible. This is false. Why? Because as I perturb the kink, which is odd, by a general U0, U1, it will start to move because this PDE is translation invariant. In fact, it's Lorentz invariant. So what happens if you take a generic perturbation of the kink, it will start moving. It will have non-zero momentum. That is why I said, make them odd. Okay? When you keep the field phi odd, you kill the translation symmetry, and then this is a perfectly well-defined problem. What is known on this? Well, for sine Gordon, this is a theorem. In fact, with t minus a half, you take odd small perturbations in precisely such a class, then you have L infinity decay. But first things first, let's go to the, and again, I have to keep an eye on time. Let's go to the orbital stability. Or if you want Lyapunov stability, which is weaker than this, which is asymptotic stability. That's a theorem from 82, and it's due to Henry Harris. And I need Maciek's help here. Brzezinski. Is this correct? My pronunciation, of course, is awful. So Henry Paris Brzezinski, some approximation to the truth. Maybe there is an S here. What they showed is that if phi at 0 minus the kink, you don't need oddness assumption. So for all epsilon positive, there exists delta positive, such that if this in H1 cross L2 is less than delta, why H1 cross L2? Well, because you have it sitting here. This is L2, phi x is L1, but then you might say, well, where does the L2 component come from? Well, in phi x, this is just H dot 1, H1, because you will get an, as you will see in a moment, you actually get a mass term also out of this. So if this is small perturbation of the kink, and by the way, you can replace this kink also with 0, but not for phi 4, by vacuum solutions, by -101. It applies just the same. And it's easier, so the kink is more interesting. Then phi of t dot minus k dot minus y in, say, H1, and I'll omit the time derivative here. We should be in phase space. This is phase space, phi t, right? In phi in R is less than epsilon. This is absolutely essential that you mod out the translation symmetry. That is why you take an inf over this parameter. So in other words, if you start near the topological soliton at time 0, in the best possible sense in energy, then you remain close to the family of King's topological solitons near, yeah, so for all times in energy, you remain close to the whole family under translation invariance of the King. How do you prove this? By a Lyapunov functional. And this is simply given by the energy. Why? Because let's just stick to, well, I can look at the general form of this. If you linearize about that, so you replace phi by kink plus something small, So we make the ansatz that phi is k plus u. And I'm not worrying now that k is shifted or not. You will see in a moment how that comes out. Then you obtain an equation of the form h plus w double prime of phi plus, which, and this is a nonlinear term, so big O of u squared. And h will be minus partial x squared plus phi minus this mass term. And I'm making an assumption that they also had to make, which is satisfied in these particular examples, that you have the same second derivative at these potential wells. Okay, so let's say you have two potential wells, as in phi 4 is good enough. Then you want those to be equal. And I think for phi 4, so this is for phi 4, it's equal to 2. And in fact, for phi 4, you can say exactly what it is. So h plus 2 is minus del x squared minus 3 sec squared x over root 2 plus 2. And the spectrum of h plus 2 looks like this. You have a 0 eigenvalue. Then your essential spectrum, which is absolutely continuous, starts at 2. So what I'm drawing is the spectrum of h plus 2. And then you have something extremely interesting. At 3/2, you have a discrete mode. You have an eigenvalue. Of course, since this is on the line second order, all of these eigenvalues are simple. That is the spectrum of h plus 2. Why is it immediately clear that this is an eigenvalue of h plus 2? Because of translation invariance. In fact, h plus 2 k prime has to vanish. Or in other words, k prime has to be an eigenvalue of h with eigenvalue minus 2. Why is this obvious? Because you take a derivative in y of k minus y. That's the infinitesimal generative translations. Since this is translation invariant, we know k is a solution of this without the time derivative. So therefore, and the same holds for any translation by y. So therefore, you can take a derivative in y and you get minus k prime xx plus of k prime is 0, right? You get that. And that is h plus 2k prime. And you know more, you know that k looks like this, so k prime will have to look like that. So k prime is a positive because the kink is strictly increasing, a positive, nicely decaying solution. So therefore it has to be the ground state. So therefore you know that there is no negative spectrum. You can never avoid in these models the translation invariance. Then phi 4 has this internal mode. Now, why? So where is my Lyapunov functional? My Lyapunov functional is going to be the second variation of the energy, because notice that h plus 2 u is going to be coercive. And provided u is perpendicular to k prime. And that holds in particular if u is odd. But in the Henry Perez-Rzynsky theorem, we're not assuming oddness. So where do they get the coercivity condition? Well, by taking the optimal y. Then you enforce the perpendicularity, you have your orthogonality condition, your energy is strictly positive, and you have a Lyapunov functional. Okay? Now, notice that this internal mode, as it's called, is completely irrelevant for the orbital stability. But for asymptotic stability, it is extremely important. Why? Because now the time-dependent problem that underlies any attempt at addressing this open problem is as follows: UTT plus H plus 2U equals a nonlinearity of U. And for phi 4, I don't have to be so opaque about this. It is minus 3 tanh x over root 2 U squared minus U cubed. And H is completely explicit. It is right here, minus del x squared. To those of you who are familiar with the Purcell-Teller hierarchy, for both sign Gordon, the linearized operator is from the first level of the hierarchy. This is from the second level of the hierarchy. What am I talking about? There are these famous Purcell-Teller operators. H is minus del x squared minus nm plus 1 sec squared of x. Purcell-Teller. And you might say, well, n equals 2, you get 6, not 3. So did I just speak? No, because it has a different normalization. So x of root 2, if you change variables, you get the second. Why are these so remarkable? Well, I can't really go into that, but there are creation and annihilation operators for these, okay? And you can go between the levels. In fact, now let me not go there. All right, so for the asymptotic stability problem, why is this internal mode 3/2 such a disaster? First of all, it's kind of entertaining that the eigenfunction with eigenvalue 3/2 is completely explicit. H sec tanh, I should write it like this. H plus 1/2 sec tanh equals 0. And of course, the argument of sec tanh is not x, it's x over root 2. And you will see that sec tanh of x over root 2 on the linear level gives you harmonic oscillator. So if you take u of t and x is a of t, sec tanh of x over root 2, this function on the linear level is an explicit solution of this equals 0. And what is a of t? Well, the harmonic oscillator. So a of t would be a linear combination of e to the plus minus root 3/2 times t. Root 3/2, of course, comes from, you understand, from the eigenvalue 3. So why is this a problem? What am I doing here? There's an I, harmonic oscillator, so cosine sine. So there is no decay. This is just an oscillatory, highly localized in X solution. So it would immediately invalidate anything like this. For the Henry et al. Theorem, you don't care because this doesn't go to 0. That's the big difference between orbital and asymptotic stability. What's known about this open problem? Well, 2 years ago, Delors and Masmoudi published a 300-page book in the EMS where they try to address this problem. It's a heroic effort, and they don't go to time infinity. They go, this is epsilon, right? They go to time, so time less than epsilon to the minus 3.9999. Okay? So up to long times, if you wish, in the size of the perturbation. And again, this is a heroic effort spanning 300 pages, a book in some EMS series. It has a wonderful introduction. If you're at all interested in these circle of problems, please read the introduction. So this seems to be a hard problem. And you might say, well, how do you get out of this conundrum that I shouldn't be speaking about a problem that's an open problem, right? But as if I had much to say about it. This harmonic oscillator doesn't decay. You will ask me, how do you get around that? Well, via the Fermi golden rule, because there is a nonlinear coupling coming from this that couples this mode to the continuous spectrum. Not surprisingly, the frequency is, the energy is twice root 3/2, which of course is bigger than 2. Where does this come from? Well, the frequency of oscillation, as you can see, is root 3/2. U squared doubles this frequency. And therefore you end up with a Fermi-Golden rule effect, the coupling to the continuous spectrum. So I could spend much more time on this, but I really want to go to something else, which is a problem that we have been struggling with. But I would be completely amiss not to mention a positive result on asymptotic stability, not for phi-4, of course, but for sine Gordon. So as I said, sine Gordon is completely integrable. So you will say, can you address it with inverse scattering transform? Yes. And you might think this was done 40 years ago. No, it was actually only done 3 years ago, 4 years ago by Chen Liu. So if you're interested in that, here's Chen. This is Gong Chen at Georgia Tech. And this is 2020, where they obtained a much stronger result than just asymptotic stability of the king for sine Gordon. They proved for generic data, what generic means, please look there. It has some interpretation in complex analysis because they employed d-bar, steepest descent. So they obtained soliton resolution for sine Gordon. What does that mean? Your solution disintegrates into moving kings, anti-kings, and breathers, but they don't allow the wobbling kings. So kings and breathers, everything Lorentz transform, superposition, and free radiation. There is another aspect to these problems that is absolutely essential, which is you can't approach them naively and say you hope to prove scattering, meaning that your solution becomes the king plus free radiation. Free radiation would mean that you behave asymptotically like a solution to a wave equation without potential and nonlinearity. Or in fact, you should keep the potential, but not the nonlinearity, I suppose. And that would, so that is completely false because this is a long range type nonlinearity. The free decay of just Klein-Gordon, linear Klein-Gordon, is 1/√t on the line. That means that if you write this as u squared u squared decays like 1/t. That means you are borderline long range. And you need a phase correction of e to the I log t times a certain function w. And so this log is the famous long range effect that these models have. So they are difficult from many angles. Then Luhrmann and I in 21, we avoided any kind of, on purpose because of phi-4, completely integrable techniques, and we proved asymptotic stability for sine Gordon kink for all perturbation. I wish I could go into the kind of failure of the Fermi-Golden rule. That's a null form that underlies why we could do this. There's a normal form analysis, and it is also rooted in the space-time resonance method of Wilhelm Schlag and Chatal. But instead of doing all that, I'll speak about a non-self-adjoint problem that we're struggling with at the moment. So if any of you have insight into this, I'll pick you to hear this. So I'm working with Luhrmann, Texas A&M, and Zurich Shoshimani. At Amherst. This project we started a year ago, and it's been slow going. Now, this is not a two-dimensional problem. Sorry, this is not a one-dimensional problem. It's a two-dimensional problem. This is Gross-Witeriewski. And the stationary form is Ginzburg-Landau, as far as I know. And this stationary form, when you omit this time derivative, so just look at Ginzburg-Landau, they admit certain special vortex solutions. So e to the I theta rho of r, and we can call them rho n of r if we stick an n here, n is greater equal 1. And these profiles rho look like this. They of course have to approach 1 because of this. The conserved energy here is rad psi squared. So for the dynamical problem, This is the conserved energy. The integral over R2. Note that these vortex solutions have infinite energy. Why? Because the angular derivative will lead to a divergence of this form. RdR, that's the measure in the plane. This is infinite. 1 over R squared comes from the angular derivative of this component. So all of these vortex solutions have infinite energy. Nevertheless, they're of interest to the physicists. And only recently was the orbital stability of vortex solutions established for Gross-Bitaevsky. In analogy to this, albeit it is much harder because the energy is infinite. So who are the authors? Forgive my poor pronunciation, Smets. And maybe somebody can help me here. There is a third name. I'm deeply ashamed that I don't remember. And this appeared not long ago, maybe around 20. And so they established orbital stability of these vortex by renormalizing the energy in a suitable form. So they do indeed remove this divergence from the definition of the energy and then establish orbital stability. Now, what we three did, and that's probably an example of fools rush in where angels fear to tread, is to look at asymptotic stability of vortices. If you do that, you obtain a matrix operator in analogy to these linearized operators that drive this asymptotic analysis. We now have a matrix operator because what we do is we write psi as the vortex V plus some correction U, which is small, and we write this U as, say, alpha plus I beta, where alpha beta are real, needless to say, and then the I switches their role, right? Interchanges these, the I, and therefore you have a linearized operator of this form where L1 and L2 are of Bessel type. What this means is that this is that right? So it's rho 1 squared minus 1. That looks right, yes. And n equals 1, not that this matters for us, and I should have emphasized, we stay in the equivariance class, meaning that our U is a U of time and radius, but not angle, all right? So therefore, we actually reduce ourselves to a problem on the half-line, the radius r, albeit it's non-self-adjoint. And we know that rho 1 of r has a certain asymptotic behavior. It's some constant a as a times r, as r tends to 0. And it is 1 minus 1 over 2 r squared plus big O 1 over r to the 4 as r tends to infinity. So, as crazy as it sounds, our goal is, because asymptotic stability typically means L infinity, what we would like to do is understand the decay properties of e to the TL applied to some nice, say, vector Schwartz function, L infinity. All right. And so, of course, everything has to be driven by its behavior as time tends to plus infinity. And as insane as it sounds, we want to develop, or rather approach this question via a suitable distorted Fourier transform. Now notice how insane this is, because L is not self-adjoint. It is J self-adjoint, so to experts in grind space theory, you do have this property where J is symplectic, but that doesn't seem to help us. So in 5 minutes, I will attempt to tell you what.
Is TL or UTL?
Very good question. We can prove, and that's one of the theorems we actually can establish, that the spectrum of L is on the imaginary axis. So therefore, we view this as e to the minus IT IL, and IL as real spectrum, so then this is meaningful. But you hit kind of on a very important point. I will show you very quickly why you might expect that.
Okay.
In fact, let's look at the caricature of this. So how does this behave? Well, at infinity, to address your question, right, you will grant me that somehow we look at R tending to infinity because that's what the bulk of the spectrum, the essential spectrum, should be characterized by. So at infinity, L1 is of the form minus dr squared minus 1/4 r squared, and L2 will be this plus 2, no? Plus 2 minus 1/4 r squared. Plus corrections that decay like 1/r⁴. And so what does the spectrum of L1 look like? Of this Bessel operator, it's just 0 to infinity. Okay? And so then let's replace this by xi squared. L1 is a non-negative operator. So let's replace it by xi squared, and let's put down here xi squared minus 2, 0, all this matrix A. And so where is the spectrum of this matrix? So we have to look at the characteristic equation. Well, it's like an undergrad exercise that I will struggle with. So you have z squared is xi squared, 2 plus xi squared. And so z is then xi plus minus √2 plus xi squared. Xi is real, so you'll see the spectrum is real, but for non-trivial reasons. So your question was absolutely justified. And moreover, you see something very curious, that the spectrum should go all the way down to 0. So since I'm kind of running out of time, I'm scrambling to tell you something that we're both certain of because we proved it. So here is a theorem. And I'll be delighted to hear from any of you thoughts on how you would think about this.
But you said the spectrum is
The minus missing.
Okay, where's my minus missing? You saved me. You saved me somewhere.
Right.
Minus, yes. Thank you. Thank you. You see, I failed my undergrad exercise. So the theorem that we proved is that on a suitable domain, since we're dealing with a non-Cephaljoint operator, it's hard to wave your hands. You really have to be patient and do things nobody wants to do. What's the correct domain? But the spectrum of L sits in IR. Moreover, we want to use the Hilliard theorem because what else is there for non-Cephaljoint operators? We're lacking some kind of systematic theory, but we do have this. And that is not terribly hard to establish. So therefore, and again, this is, we can identify the domain on which this L is closed, all right? Close this, you have this bound Hilliard, which is a very forgiving theorem in terms of its assumptions, therefore shows that this is like that, okay? But you see, I spent all this time before on resonances at thresholds, and unfortunately then didn't really have the time to go into all of these operators that are here have threshold resonances, all of them. Each of these partial teller have threshold resonances. They permeate this nonlinear analysis. And in fact, their presence in these field theory models held up the asymptotic stability theory of King's for many years, and only over the past, say, 4 years, 5 years, has this changed. But here in this non-Cephaljoint context, what does this have to do with the resonance? Well, this is actually a very interesting phenomenon because Ross-Pitajewski has a gauge freedom. If you can change this angle theta just by rotation, you can multiply by e to the I gamma. And what happens then is that this gauge freedom produces a zero mode, just like the translated kink is a zero mode. So here we have the following. L, and of course, I removed the first order derivative that sits in the 2D Laplacian by conjugation by √r. So rho 1 is rho, this is 0, 0. Because this function sits in the kernel. In fact, L1 does have a 0 resonance. L1 is in the sense of Weil, its limit point at 0. You have a branch that diverges like r minus a half, and you have a branch that behaves like r to the 3/2 near 0. Then you have one that grows like root r, and you have another one that grows like root r log r. That's the behavior of Hankel function 0, because you have a 2D solvent. And so you have a branch that's globally subordinate. And so in this sense, it's legitimate to speak of a 0 resonance for L1. Now for the matrix operator, you then have this. And then another undergraduate fact, you have a nilpotent form. You have a nilpotent component in your Jordan form because the kernel of L squared is strictly bigger than the kernel of L. And here it is. Okay. Now, do you remember from linear algebra ODEs, the secular modes? What happens if you take a 2x2 matrix with a nilpotent part? Jordan form, right? If the kernel of L squared is bigger than the kernel of L, you have a 1 off the diagonal. What is e to the TA for this? Forgive me this silliness. It's identity. It's this. Okay, so your Jordan form, your nilpotent part produces this secular growth. Now, you will complain that this is not L2. This is not L2, exactly. So if you have an L2 theory like this, then how do you know that this might produce an effect like that? Well, this is a non-trivial question, but we can still answer it via some perturbative analysis where you truncate this, and the truncation gets larger and larger the longer the time is. And so here's another little theorem I'm happy to sketch to anyone who wants to hear it after the talk, is that this actually has to grow like T. So we do have a nilpotent phenomenon. And what we are now struggling with, and unfortunately I'm completely out of time for that, is to build a Weil-Titchmar theory for this non-self-adjoint operator in which we write this evolution. Right, Hila, you see that this is obtained by writing the resolvent as the Laplace transform of the evolution. Now you inverse Laplace transform, and you get this e to the IT lambda. Lambda is now real, and here you have the jump of the resolvent of IL. D lambda. In which sense is this to be understood? So you have these two horizontal lines. Here's the real lambda line, and then you have lambda plus IB, lambda minus IB. And when T is positive, only this contributes, not that, but you really have the jump of the resolvent. And what we now want to do is to take limit B to 0. We know how to do this formally. And it was extremely important for us to understand that this is actually a fact and not just something hypothetical based on an analogy between this and that. It is actually a fact. And so what has to happen somehow, and we have a suspicion what happens. If you call this Z, then this difference has to contain in its Laurent expansion 1 over Z squared, because the residue of e to the I tz over Z squared is IT. That's the residue. So this has to come somehow from a contour integral. Here is 0, contour integral like that, and you pick up this via residue. And for the rest, you will have your distorted Fourier transform for real lambda. But I'm out of time, and I'm happy to tell many more details about this to anyone who's interested. Thank you.
Very much for the nice talk. Are there any more questions? Some questions were not asked by Alex.
It's some sort of Sahotsky formula that you were using here.
Again? On which one?
Sahotsky. I mean, it's probably too far-fetched, but
What is the Stokowski formula?
you write 1 over x minus plus I 0. So the limit is rewritten as the
PV of 1 over x
that's right,
plus I
that's right.
delta.
Yes. Well, I mean, I understand that this is not delta, but there should be derivative in there.
Yeah,
So this kind of second order thing.
indeed, would be like a derivative of a Hilbert transform. Yeah, so it's more singular. And what we have is a formal understanding how to write this via matrix fundamental solution. So I had written what L1 does, this Bessel operator near zero, its limit point. So this whole matrix operator L is also limit point near zero in the sense that there is a matrix fundamental solution that behaves like R to the 3/2 and another one that's R minus 1/2. R minus 1/2 is excluded. That cannot appear in the Green's function for this. And at infinity, you construct a matrix Weil-Titchener solution. And then you have to deal with the Riemann surface that has 4 sheets because your matrix second order problem is actually a scalar fourth order problem. And then you use Lyapunov-Perron to build the stable, unstable manifolds depending on which sheet of your Riemann surface you're on. And the Riemann surface is parameterized by this Z. And you run into all sorts of issues. For example, the Stokes phenomenon of this harmless looking Bessel operator. In the upper half plane, there is a Stokes phenomenon. Comes up here.
Does there exist a general theory of non-self-adjoint operators with boundary conditions which would or some kind of extensions of non-self-adjoint operators that would include
I'm not aware of it. It's a very interesting question. So we are working with our bare hands because even in Krein space theory, so this is J self-adjoint, but the J self-adjointness, I don't see how it could help us here because they don't like to work in pairs of Banach spaces. Remember Howland's razor. It says that a resonance cannot be detected in a single Hilbert space. Yeah, that's exactly what's going on here. This steps outside of L2. So you have to work with several spaces at the same time. And another feature that's completely unfamiliar to us, I worked on matrix non-self-adjoint operators 20 years ago. However, asymptotically, they were self-adjoint. Asymptotically, this is not self-adjoint. Doesn't do you the favor. And so you have both non-self-adjointness at 0 and at infinity. But at infinity, you have this phenomenon that you can build everything, or you have to actually, off of this Bessel. First, we try to put this in a big O, hopeless. You can't do the matching. You can't do your connection problem. You have to include this term. And it turns out to just be barely enough to do a matching. But now we're struggling to extract the 1 over z squared singularity. And we are facing a monster, which is called Écart's resurgence theory, asymptotics beyond all orders, because this 1 over z squared for us is the moment is hiding in the difference of 2 exponentially large terms. 2 exponentially large terms, and we have to do cancellation to infinite order, or we're missing something completely. Okay? But this monster of resurgence theory scares me. That's where we're at.